Here we go, and let's present slides. And I've got Nick's cats today. But, so anyway, let's get underway. And so welcome back. I hope you had a good break. That we're back in the saddle again. We've got a test coming up Friday, and it's on chapters 5 and 6. I've got a draft of the test ready, but we're going back through revisions on it. A number of the questions we've thrown out and trying to revise them, make them somewhat clearer. And hopefully I don't have the same problem I did in test 2, where I guess my expectations were a bit beyond what you were going to pull off. It's harder to judge with multiple choice. That with math type questions, I can gauge that almost perfectly, but with multiple choice, it's trickier. It's really hard to get with a math test. Getting over 90 is quite attainable if you design it well, and so I expect to get a good number of students. Not a huge number, but a good number that are over 90% on a test. With multiple choice, that turns out to be designing a test where you think your top students will get at most 1 to 2 wrong. And it's so easy to get 1 or 2 wrong, just, you're close but not quite. So I almost wonder, should you have 100, that if you had 16 questions, maybe you should be marking it out of 14, because of those. You got a real truncation there that you don't get with a math test where you got part marks and that type of thing. What you probably saw in Quant 1, that I haven't seen any advice on design of multiple choice for grading. I'm still building your next assignment. I've got to get it ready by the mid to late this week. It's building you a data set, trying to create a new one for you that uses, again, real data. Feedback from last term was students liked it when they had data that they could relate to in some fashion, or it was because I'm not using survey data. We're going to be doing some regression analysis, and your survey isn't. The relationships are just too weak. That anyway, we'll get into the regression bit today, and you'll start seeing it. So last week was beautiful. That the lakes around Halifax, everybody out skating. This one is near me. It's called Frog Pond, Fleming Park, where the dingle is, if you know that side of the Northwest Arm. And Dora and I were out for our walk. There must have been 100 people out there skating. Cars parked everywhere. And the ice surface wasn't perfect. It was a little bumpy, but still, everybody wanted to get out. And and I've heard reports from almost everywhere where there is relatively shallow lakes, generally because they freeze quickly, that they are in excellent shape for skating. And, very good surfaces. I don't skate myself. I'm too much of a klutz on a pair of skates. So, again, where are we, if you can remember that far back? We were sort of bumbling through a couple of classes, and it's sort of after doing pivot tables where it's very intense and doing an awful lot of stuff quickly. Uh, in some respects, it sort of slowed down the pace in a little bit of theory. That we were working at trying to develop models. So if you're going to take action based upon your data, you need something to give you direction of what action to take. And that's especially the case when we get into models and predictive models, where it's going to predict the outcome. If you do this and this and this, or if you, this customer you pick, how are they going to behave? And predictive models are really good at informing action. If you did Quant 1, you did prescriptive models. Linear programming told you exactly what to do. In our stuff, we aren't going to do prescriptive models. It's not going to actually tell you the action, but it will inform you of the consequences of your actions. It's sort of more like a descriptive model, but it's predicting an outcome. And that the one we were looking at was predicting credit card balances, and the based upon customer characteristics, and talked about if you're going to build a model to predict a credit card balance, you would want to pick the best model and one that gave the best predictions. And we define best in terms of the not only were the errors, the prediction errors, as small as we could get them in an average sense. Some predictions are going to be very close, and some are going to be way off. But we wanted to add a bigger penalty to the ones that are very far off. That big errors could be catastrophic, whereas small errors we can deal with. And so what we did was we squared the size of the error. So if the prediction error is going to be big, if it was twice as big, then the penalty we're going to assign is 4 times as big. We're going to square things. And that will discourage us from having a line that has many really big mistakes in it. But it may have an awful lot of small mistakes. But we figure we can manage the small ones. It also made the math easier. That doesn't matter to us because we're using Excel and it'll do all the hard work for us. But in fact, with many types of modeling situations and data analysis problems, years ago, even when you had access to a computer to do the calculations for you, if you're using a method that was very computationally intensive, we sometimes couldn't do it. So we couldn't use huge data sets or some complex tools. And so it was nice to have a tool that was manageable with a large data set, and it was reasonably quick and efficient in that regard. So what we're going to do is use Excel to fit the model. We're going to try to interpret what the model means, and I'm going to hammer you away on that. You've already gone through chapter 6 and you've had some questions associated with that. No sense building a model if it's just a black box. There are some tools used in data mining that are black box. The data goes in, something gets processed, and something comes out the other end. What happens in between, we have absolutely no idea. Can't explain it to ourselves, can't explain it to anybody else, but we know it's a method that works well. I don't like those. I'd like to have a sense of what's going on and why it's working and why it's not working. It's in part a matter of trust and transparency. And if it's transparent, you're more willing to trust it. And so at the very least, seeing the model, how it calculated that as I said, that we've sort of talked about the principles, but actually seeing the formula being used is important, at least to me. And they're good if we want to do causal analysis. Why does this change that? What's happening here? That's that sort of cause and effect type idea. We'd like to look at trying to understand accuracy. And we've said it's supposed to be the model gives us the most accurate results. But when we go to use it, we've got to convince those that are going to use our results how accurate our results are. And we need a way of communicating that. And there are 2 methods we're going to use. One, standard error, a term we sort of referred to before. And another is called R squared, which is, in my mind, somewhat abstract, but it's really popular. So many people like R square and they don't pay attention to standard error. I'm the reverse, but we'll get to it. But that's all we're going to get through today. We're going to build in the next class, get into building complex models, and we'll have 2 relatively intensive classes for chapter 7, and then the pace slows down a little bit again. So what do we mean by a model? We're going to talk of models as formulas. Not all models are formulas. You can make a physical model, a picture, those are models. You can have a verbal model. But this is a model that's a formula. And we're going to use, I believe, quite strongly in the KISS principle. KISS, Kiss, keep it simple, stupid. Keep it as simple as possible. And it's not just that that's good for communication to others. We make fewer mistakes with things that are very simple, simple design principles. That it also tends to build models that are more robust. They don't break as easily. They're not as fragile. If you throw something at it, it doesn't fall apart. And as a design principle with a whole bunch of different things, not just formulas, keeping it really simple is often a very, very good strategy. So what we're going to do is start with as simple a model as we can, and we'll add complexity incrementally and keep adding it as we feel it's needed, but only if we feel it's needed. We're not going to add extras just because, oh, this is the thing to do. No. So if I'm going to give you a formula, the simplest formula I can build is a straight line. And that's what you saw in Quant 1 was models that involved straight lines. When you did break even, when you did linear programming, if you remember the finance stuff, those formulas were complicated. Try to stay away from them if you can. So we're going to stick with the very simple ones of a simple straight line. And the key thing here is trying to figure out what variables to pick and how to pick the numbers. So here I've got a model that I suggested before the break was to say, let's predict balance based upon rating, because rating had the strongest correlation, linear correlation, and it's a linear model, straight line correlation. So it's the best variable to use. But how do you pick the slope? How do you pick the intercept? You're not given those numbers. Whereas in Quant 1, you had a break-even model and you were given the fixed cost, and you were given the variable cost. What if you aren't given those sorts of things and you do it based upon your experience of making something, and you made a certain number of units and you totaled up your costs, you made some more units and you totaled up your cost, and you went back and forth and then said, can I build a formula that fits the data I've seen? So how do we do that in Excel? And I forgot to open up the file for today. Let me just go and see if I can find it. I may have it here in Top Hat. Excuse me. Nope, that's not where I want to go. I'm going to get out of my presentation if I do that. Let me go back where I was. Do. Let me go and find my courses here. Where are we? And, oh, I think I'm actually going to go back this way. Where are we? There we are. I want chapter 6 data. So this was the data we had, okay? And we had looked last class at taking the rating data. I'm just going to take this from last class. And we had the balance data. Let me just put this into a new sheet. And this is a recommendation I'd make with, excuse me. If you are building models, regression models, because of certain quirks within, see me, excuse me. I'll get here. Here we go. Certain quirks within Excel, and also because you may be experimenting with lots of models. Let's try this, let's try this, let's try this. And it isn't a bad idea to save each of the attempts you make. Sort of like with a pivot table where you, like assignment 2, you swap things back and forth, back and forth. If you wanted to go back and, well, what was the table I had for question 3? Well, you have to go back and recreate it. That How about if for this experiment that I'm going to build a model, and we're going to see this in our particularly chapter 7, this is the data I want to use. So I'll put that in a new sheet. I'm going to build a model, and I'm going to put the results of the model in the same sheet. So with this one, if you recall, here was our data. And if I could have gone and let's just make sure I remember what it looks like. I had a scatter chart that looked like this. Okay. Maybe I should make this a little bit smaller so we can see it better. So that was our scatter chart. We're putting a line through this. Now, I'm going to show you the cheater's way of doing that with a simple model that where I don't have to get into regression. If you're in a scatter chart, you're in design, okay? Go over here and it has quick layout. And these give you different layouts to your chart. And it's mainly putting information in different spots on it. But there are ones that have lines in them. There's one here that has a line. It just gives me a little dotted line. And then there's another one down here that gives me a line. I'm going to click that one. Okay. I don't like this stuff and I throw it out. It takes up too much space. And I don't like my little dotted blue line because I can't see very well. And I like to put in a solid one, and I like to make it thick. You've seen me doing this stuff before. So this is going to be the line I'm going to put through this data set. And before I was saying I'm going to try to find the equation of this line, well, you probably can't see this. Let me make it bigger. Hopefully you can see that. This is going to become the equation of the line. X, this is my x-axis here, is the rating. And over here, it's the balance. And I think I told you I don't like reading that way, so I format my axis. And I'd like to rotate it so it's horizontal. You don't have to do this. I may ask you to do something on assignment, but this is just personal preference. And so here's my line going up. So if you recall, generally we put X on the horizontal axis, Y on the vertical axis. So this one says that that line is 2.566 times rating times X. That's X here. See? And so that's what rating is. And minus 390. So if I extended this line downwards, it would intersect down at 390. So actually, I'm going to go and do that. I'm going to draw a line on top of it, just so you can see it, because we're going to go back and look at this guy in a minute. So line that up a little better, same color, make it thick. There we go. So this number here, the 390, okay, give you a, I want to make you green. That's not dark enough. I'll make it purple. That's right down here, down at the bottom. That's the intercept. So that's your intercept, and this is your slope. And we'll get back and talk about these a fair bit. This is what I want to build. That and Excel gives me, by looking at this quick layout, a quick and simple way of getting that equation of a line. Use it in little simple problems where you want to go through and do this quickly. In practice, though, you should be using a different tool, using one of the data analysis tools. So let's go back here. Let me go over to data. And I'm going to go to data analysis. There we are. So I know it's very tiny print, but down here there's one in the list called regression. It's an old term. It had to do with one of the earliest papers about this actual mathematical technique. And it was a word used in the paper, and it stuck for describing the technique, and they call it regression. So what does it want? It asks, where is the y variable? The y variable here is balance. It's what you're trying to predict. So in my case, that's in column B, starting in the first row where the label is, and it goes all the way down to row 401, because there's 401 values in this table. If you scroll down, you can see them. My x range is what I'm using to predict. And so I'm using just rating. It's in column A and goes as far as A401. And I've got labels to my columns. And generally I like it with labels in there. It helps me read the results it's going to give back to me. Never use the constant as zero. That's way beyond our understanding of the material. It really changes a whole bunch of things. I'd recommend you stay away from that. We don't need confidence level. Again, that's stuff we don't need. Normally, I'd put it in a new worksheet, but this time I'm going to put it all in one space. So I'm going to put it says output range, where I'm going to put it down here. So let me put it down in D16. Just tell it the starting corner, top left corner of where you want your output to be put. At the moment, in the next class, I'm going to be looking at this thing called residuals. For today, I'm not going to touch them, but in future we will. And sometimes you'll use these various plots that it has available to us. If I've done it all correctly, and I click OK, this should work. And it did. There's some stuff down here. Just a couple of cautions on this. If I had a blank, see this one that has a 0, suppose it was a blank, I could still do a scatter plot, and this would still work. It would calculate a line for me. So blanks I can still do plots with. But if I use the regression formula, if I have any blanks there, it will crash. It will not work. It will treat a blank as a text, and the regression tool must use only numeric data. We can have no blanks in our data set. That I can't emphasize this enough. So if you want to go and look at the survey data that you had, why did I choose? I'll get that one in a second. That if you use the survey data that you use for assignment 1 and 2, you can do a scatter plot of high school average and grade point average. Okay, so what was your high school average, self-reported? What was your grade point average? And you're going to get a scatter plot. It's just, they're all over the place. But you won't be able to find correlation, and you won't be able to fit a line because some students didn't give us both values. You would have to go and filter out all the blanks, then copy the data into a new sheet where it's nice and clean, and then do your analysis. But you could do a scatter plot with the blanks there. And actually, if you requested this chart layout with this formula, it would do it. It would filter out the blanks for you. At least it's done it for me in the past. But if you went to use this regression tool to see, well, what's the relationship between high school grades and grade point average, you'll find that regression won't work because the blanks will mess you up. Just a caution. I know it's not in the notes, but anyway. So if I backtrack here, when I did data analysis, regression, and filled in the spaces, it asked, where did I want the results put? Because this will do some analysis and then it'll dump the results. And I can put it in a location, I could put it in a new worksheet, or I can make a whole new workbook and put it in there. Um, just for convenience, I'm keeping everything about this example in one place. And I just picked an open space. If there's already stuff where you put it, so if I told it, oh, put it in A1, it would say, whoa, but there's already stuff there. Do you really want to write on top? So I look for a blank space that's not too far away. So that was what I did there. But this is keeping everything in one place for me, which is convenient. Now, the columns, the first column and the second column actually have a lot of words in them. So I'm going to make them wider. Okay? So we can study this. Let me just double check to make sure I've got everything in my slides here. So I told you about this, filling it in, and I'd fill that in. Okay, and then here are the results. So this is the results I'm going to get out of my spreadsheet. And this copy, I've annotated it. I put some stuff in it. Because, see, with mine that I get here, it looks like this. Okay, no extra notes to it, but it should be the same as what's in my slide. So let me use my slide for a minute. It gives me 3 blocks of information. And I've described these as the first one I use to give me insights about, is the model any good? Should I use it? Without even looking down to the details and the specifics. What's the overall quality of the result? And this is often the first thing people look at. And they say, how am I doing? And in the next 2 classes, we'll look at improving the model. And we'll say, well, is it better? Is it better than I was before? How do you mean better? How are you evaluating performance? And so it's nice to have a block with that. Different people look at different things. So it's got some stuff that for me is clutter. But we'll talk about that. The second block is an old traditional piece. And it reminds me really when we did everything by hand and how we did calculations and do statistical analyses. And in stats, there's a bunch of theory and a bunch of principles about evaluating whether or not certain, uh, a lot of statistics is about trials, like criminal trials, where you've got to prove things beyond a reasonable doubt. And how do you do that sort of proof, and what constitutes proof, and what's reasonable doubt, and defining those sorts of things. But it's done mathematically. But that is really what a huge chunk of statistics is about. And it's for different types of trials. That how do you do it in a murder case versus an armed robbery case versus an assault case or something like that. Maybe you have different types of evidence and you use different tools. Okay. And this was a table that we used to summarize our calculations when we did it. And you'll see this when you take a stats course. To be honest, I don't see much use for it anymore. But I lived with these things for years, ate them for breakfast. The other one, though, is a useful one. And the stuff I bolded is the most important. The first thing it tells you is the coefficients of your model. So here it says the intercept is the minus 390 and the slope is the 2.56624. And if we go back to the slide I gave you, oh, I didn't have it here. No, I had it, I showed you it in Excel. This model up here. Oops, excuse me. This line. Notice minus 390.85 is my intercept, and this is the slope of the line. So that output that comes down in here, this is the intercept, that's the slope. This is the calculations or a summary of the calculations that go into the model, and this is what the formula becomes. So that if I was to write out my model now, and let me write it out longhand, I'm going to say balance, oops, I'm actually going to say estimated average balance is equal to minus $390.85 plus, roll across here a little bit, oops, excuse me, my coefficient, 2.5662, if you want to put in all the decimals, times what the rating is. Oops. So these are the numbers that go into my formula of the line that I've got up here, the formula of that line. And there is a standard error associated with it. You may notice up here, there's also a standard error. These terms we'll look at, and we'll look at them a little bit later. But first off, this tells me the basic information about my model. All of this stuff over here, don't bother with it. You don't need it. This is the really important stuff. If you have these two things, you have really everything you really need. And even you can do the statistical stuff just with these pieces here. You don't need all this stuff up here. You don't need some of the stuff up there. So this is generally the first bit I want when I want to study the model and try to understand what's going on. And then what do I mean by these sorts of things? And why did I add estimated and average and not just say balance equals this stuff? Well, a couple of things. The understanding the numbers first, and then I'll look at interpreting those other words. The intercept is minus 390. Think of a cost function when you did break-even analysis. Total cost was equal to fixed cost plus unit cost times number of units. So the intercept was fixed cost, the slope was the cost per unit. That fixed cost is the cost when you're not making anything. It's your startup cost, that you're not doing any activity at all, but you're incurring a cost. So it's when x, your x variable is equal to 0, what's the balance? So if I'm looking at my formula here, if rating was 0, this term would disappear, and I've just got estimated average balance is minus $390. If I'm looking at my picture, it's, oops, sorry, see, I messed things up when I played around with changing columns here. Down here, that's my intercept. So if the rating was 0, the balance is minus $390. What does that mean? How do you get a balance of minus $390 on your credit card? Any thoughts? No, I don't owe a thing. It's no debt. No, I didn't overspend. Yeah, they owe me. That I try to pay off my balance each month, and so it should be 0 if I haven't spent anything in the next month. But I can remember one occasion where I returned the item and got a credit back again. And so the next month, my balance came back as minus $300 because I got a credit back onto my account. So the bank owed me $300. I could go spend $300 and not owe anything because I've already got a credit there. And that seems strange. Now remember, ratings, the better the rating, the better your credit, the better customer you are. You'll notice we have no values down here at all. Would a bank give a credit card to someone whose rating is 0? It means that they are hopeless risk. There's just no way they're ever going to pay anything back. I should never touch them. They are the most risky people in the world. They probably declared bankruptcy multiple times. That if your credit rating is 0, no one will give you a credit card. That, and basically, if someone had a rating below 100, they didn't have a credit card. That, but why do I have a number of minus 390? It's because I need a number to make the line. Just from this simple mathematical perspective, not thinking about what it means. I want to draw a line through the scatter. Well, my line happens to go through and hit a negative value. I'm never going to operate down here. Generally, if you're building a regression model, this range of about 100 up to about 1,000 is your full experience. You've never seen someone with a credit rating below 100 or above 1,000. So I really don't know what happens there. I've never been there before. It's a strange country. Never been to. This is where I've traveled, and I'm summarizing where I've traveled. So I should only be using this line over that range where I've traveled, and I have some experience about. So I shouldn't be using it down here anyway, but I need a number for the formula. So that's all it is. And often the intercept gives you a stupid number, a number that makes no sense at all because you're never going to be there, but we need the number in a formula. In fact, I get silly numbers with ratings below 150 because that's when it starts going. And it's because these were all people with zero balances. They're almost all of them. And but to get my form, so even I said I shouldn't go above 1,000 or below 100. I probably shouldn't go below 200 or above about 800 because I really don't know very much out there. I have very little information. So here's the first caution in using regression. Don't venture into places you've never been. Regression is a way of having a formula over what you know, not for places you don't know. That, oops, I'm in Excel and not my slides. They, so again, be careful about that. Oh, I had a chart here. So don't use it down here. It's dangerous territory. So what's the slope? I've rounded it off. I like to round off numbers. I think you've probably seen that. I don't like a lot of digits. 3 digits is probably more than enough detail for me. So my slope is 2.57. What does that mean? That think of, if you can't remember slope and intercept, think of a simple cost function in break even. Intercept was fixed costs when you're not doing any activity. Okay, so here my intercept is balance when I don't have any rating. And the slope is how much you go up or you go down if it's downward sloping if you move one step on the x-axis. So in a cost function, that was if you were to make one more unit, how much would your cost go up? That was your unit cost per unit. In this one, if my credit score went from 500 to 501, I should expect my balance to increase on average by $2.57. Or if I had two customers, one with a credit rating of 500, one with 600, or I had two groups of customers, one with 500, one with 600 is their average credit rating. On average, how big a difference is there in their balance? Well, that's 100 points. 100 times 2.57, $257. So the increase should be about 257. And this is an average. So if I look at that slide I had before, here's 500, and it looks like it's around 900 is the average balance. And here is 600, and it looks like it's around, I don't know, 1,100, 13, 1,200, somewhere in that range. So if I go up by about 100 points, I'm going to go up a balance of probably $250, $300. My model says it's actually $257. So, and if you can remember from high school, how do you find slope? It's the rise, the vertical change divided by the horizontal rise over the run. So all I'm doing is working backwards, saying if I change x by a certain amount, how much do I change y? And that's what slope is. And again, try to remember what these things are. So if I change something by a certain amount, how much should I see change in the thing I'm trying to predict? So I got, but again, it's an average. I keep stressing this average stuff. I'm talking about the line. I am not talking about the scatter. And we sort of sometimes forget that. We started with the scatter, all the little blue dots, and from the all the blue dots, we found the orange line. But then if I go to use it and apply it, then I'm going and trying to take the, I'm only going to be able to guess the orange line. Okay. And with the orange line, it's saying on average. So if I looked at 500 and I'm going to get about, oops, somehow I moved my line here, it looks like. Um, the average balance turns out to be around $900 or close to it. But that's the average. I've got customers that had balances much more than that and much less than that, actually quite a lot more and a lot less. So my predictions may not be all that accurate, even though my line may be a good representative of the average. That if I go and look at 21 customers that had a score between 480 and 520, so those are the people I've got that are around 500. Their average balance was $893. So estimating the average balance of those customers, I did a really good job of. This is great. But individual customers had balances from $250 up to, there we go, up to $1,411. So that's a big spread. That's almost $1,200 in spread. So about $600 above and below my guess. That, or at least, yeah, $500 to $600 above and below. My predictions aren't very accurate, but my line, predicting the average balance, if that was my goal, if I wasn't predicting individual customers, but I wanted to talk about customers in general, and I wanted to talk about, you know, customers that had good credit ratings versus ones that had a bad credit rating, and I'd like to know on average how much of their balance bigger, and then maybe how much more interest that I earn from them. My model is great. It seems to be doing a very good job at that. But if I'm talking about this particular customer in front of me, I'm not very good. I'm good at one task, but not the other. And that's not unusual. Our models are often really good at predicting average behavior, but not very good at predicting individual behavior. And there are many applications where I don't care about any one person. I'm making a decision that's going to affect thousands or millions of customers. And so I'm interested in the average behavior, not the person that I'm issuing the credit card today to. And so I may make mistakes with some customers, but I make good decisions with other customers. And on average, I'm doing well. And we'll talk about that sort of thing actually when we get into classification models, where it's more often we evaluate our decisions on average performance and not individuals. What's the standard error thing? Um, I like standard error. You're going to see that I love standard error. I find it really, really useful. And as you've seen me before, I like empirical rule. Even in your assignment, empirical rule didn't work because my data was really skewed. Generally, when we're talking about empirical rule uses standard deviation, it's talking about individuals. Standard error, we're more often talking about averages, but not always. But there are an awful lot of instances where empirical rule works actually very well. With a lot of raw data, it's not so good. But in a lot of models, it actually works very well. And so the coefficients in my model, I said, aren't just representing average behavior. The model is average behavior, but they're estimates of the average behavior. So how good am I at predicting the average? What if my estimates were wrong? If I had another 400 customers, put all that stuff in, ground it up inside my regression formulas, got a new coefficients out, these numbers are going to be different because I'm starting with a different bunch of 400 customers. I'd like the numbers to be similar. I'd like to get a number close to minus 390 and a number close to 2.57, but I know it's not going to be exact. So what is close? Well, here I can use empirical rule. I can say, if I did this many, many, many times over, I know I've only done it once and I'm only going to do it once, but hypothetically, if I did it many, many times, I would expect 2/3 of the estimates to be within about $29 for the intercept. And it would be rare to get an estimate that was more than $58, $60, twice the standard error away from my estimate. And with the slope, the same way. I would expect my slope may be off by 0.075, but it's unlikely to be off by more than twice that, by 0.15. And so you might want to look, well, what does that look like in terms of numbers? So the like the slope might be 2.42, might be as high as 2.72, and that's going out by 2 standard errors. So the slope, I'm saying that if your rating goes up by 1, your balance on average will go up by $2.42 or maybe $2.72. My best guess was $2.57, but it's somewhere in that range, I think. And similarly, the intercept could go off by 2 standard errors. So here's what happens with the intercept. Whoops, again, I've got a line here that somehow is moved out of space. It would be like those 2 blue lines around there. I'm not sure why this thing has scaled on me. Maybe because I've changed the scale of my image here. And same sort of thing happens with the slope. It's going to wiggle up and down, but you'll notice it doesn't wiggle that much. It's not wild swings up and down, but it could be off by a little bit. It's strange. This must have to be with the way it's just the picture. So that's one thing, is evaluating what are the coefficients. They help tell me about if I change something, what's going to happen. And we're going to be looking at more and more of that type of stuff shortly. And standard error helps tell me whether or not how precise those numbers are, those averages are. So as I said, it's the estimated average balance. That the numbers aren't perfect, they are estimates, and the numbers only tell me the average behavior, not individual behavior. So the other thing that we typically look at is what's the quality of the model. And it depends upon what you're trying to achieve. And I'm going to be looking at quality more in the sense of making individual predictions. I was trying to predict individual customers. That we've sort of just looked at quality when looking at average behavior, and it looks sort of okay. But if I want to make predictions, I want accurate predictions. And what's accurate? We said we wanted to minimize prediction errors, but we didn't say what would be a small error or a big error. Those are judgment decisions, and they'll vary depending upon your context. There isn't some universal truth for that. Suppose I wanted to make predictions of the customer's balance within $100. And am I doing that? How often am I doing that? But $100, it's going to turn out, is going to be hard for us to achieve at the moment. We'll eventually get there, but at the moment, I'd say I can't get it that accurate. I can't predict a balance that's going to be between $800 and $1,000. Get it down to that sort of narrow range. So how about within $250? Is that okay? How about within $500? Would that be okay? It's a lot easier if we don't have to be as precise. They say within $500, oh, that's a lot easier to do than it's within 200 or within 100. And making those judgments, someone has to say, well, what happens if we make a mistake in our prediction? These are not just nice to haves. If you are trying to discuss it with a client, ask them, what are the consequences going to be? What's the consequences if the prediction was off by $300 versus $100? And if they can't give you an answer to that, then they really don't know what they're talking about. If they're setting a goal, this is what I want you to achieve, you've got to challenge them. Why? Are you just wishing for something that may not be attainable or that's unrealistic? Or it's going to be very expensive? If it's going to cost us more to build a fancy model to give us super accurate predictions, there's got to be some benefit to that. And they don't have to measure it exactly, but if they don't have a good intuitive grasp of the consequences of error, then they don't know what they're doing. They haven't figured out, if you recall at the very beginning with business understanding, one of the things asked was, what is success? That, if they're setting out a goal of, I want to accurately predict credit card balances. Okay, why? What do you mean by accurate? What if we're wrong? Ask them those questions at the start, and they will help frame how much work you're going to have to do to build this model. And a lot of decision makers have very unrealistic expectations, and they don't need that accuracy that they want, that they're asking for. So we have two things in that table at the beginning where I said it gave me performance information. There are several items that are here. One of them is called multiple R. If it's simple models, this is the same as a correlation. But when you get into complex models, it becomes meaningless. So I'd recommend you skip it and don't look at it at all. I'm going to look at R square. We'll look at that second. Some people, and this dates back to my era when we had a small amount of data, it turns out as we put more variables into a model, we can make the model look like it's performing better, but in practice, it won't, because we're really distorting things by throwing all this junk in there. And so they wanted a measure of performance that took account of how many variables you're using, and they had it adjusted R square. And it made sense when you have a small data set. You'll see with this, the numbers are basically the same. And that's the case anytime you've got a relatively large data set. And 400 observations is not a big data set. So if I had 4,000, you wouldn't see the difference between those two. It would be several decimal places out. So I like to keep it simple. I'll just stick with R square. I don't need to get into this adjustment. Standard error is the one I'm going to focus on because that's the one I just looked at. Remember, I had standard error on the coefficient saying how far off they could be. Standard error here tells me how far off I should expect my predictions to be. So if I'm using this formula to make predictions balance, don't be surprised if your estimate is off by $232. Either way, 232 high, 232 low. And it may be off by as much as twice that amount, almost $500. That this isn't very good. The balances, most of them are between $0 and $1,500. The average is around 500. So my predictions are going to be off by $500. If I knew nothing, they'd probably not be off by much more than that anyway. Look at my scatter chart. So you can see the scatter is very, very wide. Yes, that people with low ratings, their balance is between $0 and $500. Those with high ratings, it might be their balance is between $1,000 and $2,000. And so it does separate those quite well. Ones in the middle, nah, not really. It's not that helpful. And if I look at my model, that if your credit score was 500, my best guess is about 900, but it could be as much as $464 more or less. That's from 424 down here up to 1,357 up here. And you'll see that's where most of the scatter is. There are some odd ones, outliers beyond that. And I don't fuss on the outliers. Don't worry about them. But that's still a pretty wide spread. And the next two classes, we're going to see how to get that number down, get it much, much smaller, get it down to something reasonable. But my predictions are going to be off by a fair amount. But a lot of people like to look at this thing called R-square. It's really, really popular. It just everybody gives you R-square. If you look at my Excel picture, here it is. It wanted to summarize this line as succinctly as possible. Minimal amount of information. Gave me the equation of the line, and it gave me the R-square, 0.7458. And that's a performance measure. And everybody uses it. Absolutely everyone thinks it is the best way to measure overall performance. It bothers me. I don't like simple things. That it's given a bigger name. Some will call it coefficient of determination, but most people just call it R-square. That's because our output says R-square instead of, and symbolically it was traditionally written as a capital R squared. That where does it come from? I'll just give you an idea of where it comes from. That and the basic idea was when evaluating how good the model is, that you're asking, should I use the model or just throw it away and guess? Those are my options right now. I don't have another model to work with. So use the formula or use nothing. Well, you don't use quite nothing. That if I told you that the average balance of all my customers was $500, customer walks in the door and you're asked to guess what their balance is, I don't know what to pick. I'd probably say, I don't know, average was 500. I think you're a 500. That's the simplest thing I've got. It's the only thing I've got. I'm not going to just pull a number out of the air because it may be a totally crazy number. Picking the average, it'll be maybe too high or too low, but it's in the middle. Right? It's my best guess. So how does this model perform compared to this simple guessing? And remember, we're looking at squared errors as being our performance measure. That's in part where the R square comes from. So I'm using the model versus the naive, ignorant model. And so here's my balance on being average. And you'll see there's a whole bunch of people below it, a whole bunch above. Now, if you're not knowing anything about their credit rating, don't be thrown off by this upward sloping bit, because your scatter would just be looking vertically at the dots. Who's below, who's above, and you've got a whole bunch that are around 500, quite a few that are between 500 and 0, and then a bunch that are scattered quite widely. So if I was looking at this as a distribution, it's very skewed. At the top end, it's got a long tail going out. But this is the middle of it. This is the average. And so is this model that much better? It's probably performance will be the same for the customers that are in the middle bundle, but my model is going to be better for people down at the bottom ratings and people with high ratings. You can see that sort of clearly here. How much better? Well, what we do is we look at how much improvement have we had? How much of the variation have we been able to explain, they say. All these scatter, but can we explain some of the scatter? So I can explain some of these because they have high credit ratings. I can explain some of these low balances because they have low credit ratings. That's my explanation. Well, how much can I explain away? So if I look at the squared errors with the model and the squared errors without the model, if the model is a lot better, this ratio is very close to 0. If the model is not very good, then these numbers will be similar and the ratio will be close to 1. Okay? It'll never be less than 1, or sorry, more than 1, because the squared error with the model is going to be always a bit smaller than the squared error without the model. So if I take this ratio, that if the ratio is really close to 0, then I've been able to eliminate a large proportion of the error. If the ratio is very close to 1, I haven't been able to eliminate very much. That they talk of it being the variation, the scatter that's been explained by the model. And in this case, the number is, I've rounded it to 2 decimals, 0.75. And people would say that this model explains 75% of the variation in card balances. It's actually the squared variation in card balances. 75%, that's a B. That sounds like a very good model. Do you think this one earned a B grade? Look back at it. That's one of the reasons I don't like it. This one has an R-square of 75%, which if you got a grade of 75%, now a lot of you are A students, and you wouldn't be happy with anything less than a 90%. But still, a 75%, that's pretty good. And do you think this model is very good? And I just said that if I was making predictions, I could be off by $500 either way, $400 either way. That doesn't strike me as being very good predictions. I wouldn't be satisfied with it. Okay. I find R square is deceptive. That I can have a relatively high R square and still have a model that's pretty awful in terms of making accurate predictions. And we'll see that as we go in the next 2 classes about trying to refine our model. It's really hard to make accurate predictions of almost anything. It's really, really challenging. So this is where we're going to leave it today, because I want to talk in future about that process of how do I build a better model. It's an art. It's not. It's not. Uh, there are methods that are automatic. I could just throw all the data in and it'll give me a model back. But I want you to understand a process for building one yourself instead of relying upon some other tool to do it for you, because there isn't a best way to do it. There are many different strategies, and I'll show you one that at least I feel comfortable with and feel I could explain to others. Okay, so excuse me. I don't know. Anyway, here we go. So we've been trying to find the equation of the model, and the equation explains what the average is for the model. Okay, and that our model gave us a good estimate of the average. I think it's a very good model for estimating average, but it was not very good for estimating individual customer balances. And you've got to think about what your application is. If it was estimating actual balances for individuals, not a good model. Averages, it is a good model. Both of those are value estimation applications. If I wanted to know why do some customers borrow more than others, I'm asking for causes. That's a causal modeling application. I can say, well, people with better credit ratings seem to borrow more. Those are the customers that borrow more. So Look for, if you want to find customers that are going to borrow more, find customers that have better credit ratings. If I wanted to know something like, we had a lot of customers that don't carry a balance on their card. If I wanted to identify those people, I'd be into a classification model. Can I estimate who are those that are not going to carry a balance versus those that are going to carry a balance? And maybe that's just splitting, saying that if their average balance is going to be lower than $100, they're probably the people that don't carry a balance. And I want to separate them. That's a classification problem. Generally, regression models aren't very good for classification models, but we'll talk about that later when we get to them. But regression is probably the most widely used method for value estimation and causal modeling. That, as I said, for classification, there are other methods, lots of other methods. Remember that anything you get out of a model are only estimates, and this is for models in general. We're just getting estimates because it's only on sample data. And standard error is usually a good clue to give us an idea of how good are our estimates that we've got here. And we've got estimates of the average, and we've got estimates of the actual balance. And both, we have two types of standard errors that we can use. The ones for coefficients, give us the ones on the estimate, and the standard error for the model as a whole to give us estimates of individual customers. And this R-square, popular measure, make sure you're familiar with it. And you may come to like it, and you like to use it. I'm very cautious about it. But it's so widely used, you need to have a good, some people are, I think, unduly influenced, particularly people that don't do a lot of data analysis, are thrown, I find, by hearing of a good R-square, and they're really happy and they think they've got a great model, when for their actual application, it may not be. And remember, when I'm talking about performance, I'm looking at, well, how good are the predictions? And then I'm looking at, well, what is a good prediction? So do you want to get it within $100, $500, $1,000? So I'm comparing performance to your expectations. And if you don't have expectations, you can't evaluate performance because you don't know what good is. You don't know what great is. You need to have a benchmark to compare to. And if you haven't thought about that, then this isn't necessarily a good way to go. And R squared tells me nothing, absolutely nothing, about how close it is to my expectations. They're a completely different type of way of measuring things. There aren't, it's more complicated, more subtle than it may appear. So I want to improve the model, and I can do that by adding more variables, and some of the problems with that. I can also look at saying, what if I use a curve instead of a straight line? How do I deal with those zero balances, maybe? How do I use information about gender or marital status or ethnicity? That's information. Can I put that into a mathematical model? So chapter 7, the stuff we're getting into, looks at a whole bunch of different types of things you could do, and it gives you a taste of process for doing that and some of the challenges you may encounter as you're moving through those steps. And that's where we're going to end today. You guys have a good day. If you got any questions, get in touch. And I guess you'll see me on Wednesday. Okay, bye now.